So I would like to present you the problem number 3, which is called the potato apple and oranges. And actually the problem is very simple. We have the radio, we have to build the radius. We can build it with just from one potato. We have to investigate the quality of the sound depending on different fruits and vegetables, and also depending on other parameters. We have to investigate the proof which is hypothetical plans for the best fidelity of the sound, and can we make the radio transmitter. So first one, this is the video. I think everyone knows this video, but the problem, there is no actual sound. So now I have to start my plan. My plan was like that. First of all, we will investigate the electrical behavior of the potato. Next of all, we'll go for the potato principle and actually show that the potato can demodulate the signal. Next, we'll show impossible of frequency selection by potato. And next, we'll go for the radio transmitter. So first one, we'll start of the... I didn't get what is the sound. Problem. So going first, okay, going on. Electrical impedance of the potato. So first of all, to measure electrical impedance of potato is very easy. So we apply the tension here, we measure the current, and in the end we just measure the impedance. So we have something, example of our plot is something like this. And the problem is that actually in the literature we can find actually that the potato we can modulate with the RC circuit, but the problem is that the potato actually is changing all the parameters depending on the menu parameters. Important parameters is actually the volume of potato, actually the electrical spicing, and actually the electron perturbation. So going further, we want to build our model to do that, to predict all these parameters, to predict all this changing. And to do that, we built our model. Actually, it goes like that. We can discuss it further ways how it's working. Wow, it's so very good. Okay, thanks. I'm really, okay. Is it good or not? Can you, okay, I know how it's working. I think it's, okay, is this good? It's actually bad. Okay, no problem. So this is our model to predict it. We can discuss it further, but the idea is to put each time we have the line of the electric stream lines, and we'll integrate by these lines each time for all the volume of potato, and now we can predict the different dependencies, actually verify it. This is the electron spicing, so it's our model and it's fit very well. We have also the potato volume, and we have electron perturbation. So the only saving of all of this is actually that if we have just the one model of the one sale of the potato, we can predict all the parameters, how we put the electron, what is the volume of potato, and what is all possibilities of the potatoes that we can get, and this is very important. So we can control and predict that impedance. So now what is about cat potato? With cat potato, we actually expected the some capacitor. So what we want to do, as wasn't the problem, we put the plastic film, we go for back for the potato, and we expect this formula like this. So we want to just do the same thing. We measure the impedance, so we apply the tension, we measure the current, and we put actually in the end we measure the impedance of it, and this is a kind of a plot of what we get. But is it actually the capacitor or not? It's very simple to verify. We will just change the surface here. So each time we'll change the surface many times with different surface, and to verify it, we'll just go for one frequency. Okay, we go for this frequency, and what we get in the end, we have this is our data points, and this is our theoretical prediction. So what we get, this is just a capacity model. We can predict changing, and so we can predict what is happening with cat potato. So now we know all about potato, all the possibilities that you can get, all the parameters. So you can even cat potatoes many times. I don't think I need this slide. This slide I need it. So we actually what we get in the end. Next, we try with the many types of different types of vegetable, fruits and vegetables. We get many of them, and it's the same thing. We have from just one measure. We can predict for all the volumes and for the electron perturbations and for all kind of setup. We can predict it. So now about radio. What is the radio? Why we need it? How does it work? So the first one, we have some modulation of the radio. To demodulate the radio, we put our signal, this is our sound, we use the carrier frequency. Next, we multiply it, so use IM frequency. We can discuss further, we don't use the FM. And what we get to demodulate it, we have just one diode. After one diode, we have just a positive signal. After that, we use the RC circuit to move unwanted carrier frequency. And what we get in the end, we have something like this. But there is very important condition on the RC circuit. Actually, this condition is just like that. We have a condition which is just like that. We can also discuss what we have is like that and what happens is if not. But this condition prove what is the best fruits, existing fruits for fidelity of the sound, because we have this condition and we can predict all the potatoes. So we predicted the potato that we needed, we verified it experimentally, and we have our 3 best results. This is our 3 best results for different fruits or vegetables. We can actually see that the banana is the best one, but 3 of them is not bad. So this is what we get in the end. We get in the end that the fruits and vegetables are very good to demodulate the signal. And this is what where we can use the fruits and vegetables. But what about another one? About frequency selection. We have many frequencies. If we want to listen to the radio, we need the frequency. Okay, how does it work? Actually, the idea radio have the demodulation part, and also it have the signal frequency selection. So what we get this is just the RC circuit, and what we get, we have some peak, which is impedance goes very high, which is improper frequency. And what happens here with all the current, which is not equals to proper frequency, all the current goes in the left, and all the currents for all the signal which frequency equals the proper frequency, all the current goes in the demodulation part. So this is how we can hear the sounds. And this is very important. So the radio actually is the frequency selection plus demodulation part. So we proved that we can use potato to demodulation part, but can we use the potato for the frequency selection? And this is very important because so to do that, first one we want to study about the equivalent circuit of the potato. We'll do this very simple. We have the antenna on the left, we have antenna on the left, we have the diodes, next we have the potato, we prove it just like that. So next we have the diodes plus earphones, next we have the changing capacitor, just here, next we have the potato, and next we have the ground. We have the grounds, and we will just reverse the circuit. We'll just reverse the circuit, and this is the same circuit that it was before. So this is the circuit what we will consider it. So how could, as the potato is the frequency as the filter or not? To do that, we can do the simple experience with this. We'll measure the Z of this. We'll measure the impedance of this circuit. And what we get in the end we can guess, so we measure this voltage is here, and we can measure in the end, we checked experimentally that with just one potato is actually all the frequency bigger than 1 megahertz is cut. So we cannot hear all the frequency which is just bigger than 1 megahertz. So we understand that the cut potato is actually a low pass filter. Okay, we have low pass filter. Can we do high pass filter? Because we want to do the band pass. So we want to do the band pass. We understand that this is the low pass filter. This is the low pass filter. We understand the simplest low pass filter. It looks like this. It's simplest low pass filter. And for high pass filter, what's happening? It's just this one. This is the simplest high pass filter. I think we know that. So we just change the capacitor with the resistance. And we will do the same thing for potato. We'll change capacitor and resistance, and for us it's potato, and we will expect it that it will do high pass filter. And what we get, I will just I start to speak slower. So what we get in the end, because it's very important, it's what we get in the end. We have the high pass filter, we have low pass filter, we have demodulation part. And what we get in the end, we get the band pass. This is cool. Okay, what we expected with just one model. This is our model. This is what we get. So this is the connection of potato. We connect like that. Okay, kind of hard. But the prediction of it is we wanted something like this, and we can even verify experimentally, and we get something like this. And this is very important. It's very important, so we can actually do the band pass with just potato. But the problem is, as you can see, that the frequency here is not at all in the IM range. So it's not possible to listen the IM radio with potato. But as you can memorize, we actually did it with the many fruits and vegetables. Okay, we'll go for the same thing for many fruits and vegetables. This is our prediction for many fruits and vegetables, and as you can see, the carrot is very good. So the carrot is very good. We'll choose the carrot because it's the ion frequency. It's first of all, it's ion frequency. Second one, this is the we have the same experience. So the next one, we have the same experience and even verify experimentally. But the problem is that the bandpass is very low, but very high, and what is following, if we have the experiment, we have something like this. Sorry. Okay, there is no actually. This is the sound. But we can hear the sounds, but we cannot hear some frequency. Why is happening like that? Because actually what we want in the radio, we want to choose the frequency. We expect something like this, so to choose frequency that we needed. But what we did with this thing, so we can demodulate the signal, but we just listen all the frequencies. So this is why we have this noise in the ends. And we have 1 minute, okay, no problem. So it's not possible to choose frequency with the frozen vegetables, and this is very important. And because we need actually the second order circuit. This is all the first order circuit, and to the bandpass filter, we need actually a second order first circuit. So this is impossible due to the separate frequency simulation with the potato. So going for the radio transmitter, we'll go fast. So this is the circuit for the radio transmitter. What we wanted, there is no two elements that we can get. So there is no analogy for inductor, there is no analogy for resistor, but the very important parameter. So it's very important that more experience that we show, actually we prove that if we cook the potato, for 20 minutes, we get in the end just resistance and there is no capacitor influence, so it's just resistance. So I'll go for just summary. So experientially, we did the model, we measured the impedance for each potato, we provide the model to how we can predict all of them. The same thing we did with the cut potato. For frequency selection, we can show that there is possibility to do the bandpass, but the problem is that we cannot actually choose the frequency. We choose the frequency. Very good. For the demodulation part, we just show the condition of the demodulation, and so this is our solution. Okay, good. If its quality was yes, it depends on different geometrical tolerances. This is our best fruits, banana is the best. What's the quantical plants that we could provide? We need the tactons. So this is what we needed, and yes, we can possibly do the radio transmitter. Thanks for your attention.